So one version of the molecule is that the H's and the Cl's are pointing in different directions. One is pointing upwards, the other one is pointing downwards. The other version is that the Cl's one side is switched, and this is a completely different molecule. Okay, it's completely different from this one. So the Cl is pointing downwards over here, the Cl is pointing upwards. So that's a trans version of the molecule. Mohammed, Ethan, is this clear? Isaiah, is this clear?
Yep.
Yes.
Yes, sir.
Acha, so I'm going to do more examples of this to find out or locate. And did I mention that it has to be non-cyclic? As the reason it has to be non-cyclic is, I'm also going to just tell you that quickly, that non-cyclic molecules, their double bonds are already locked in position. They can't be switched. Like if you have a molecule like this, and there are hydrogens, and the rest are, this is the carbon chain, right? So the angle would be exactly 120 degrees. So this bond over here and there's this bond over here, a carbon chain on this side. So it is fulfilling the conditions that on one side there's a hydrogen atom and on the other side there's a carbon chain. And the same is true over here, that both sides should be different. So on one side there's a carbon chain, on the other side there's an H. But this molecule can only exist in one version because you can't really, I mean, there can't be another molecule where this side is switched, right? I mean, that can't happen. I mean, you can't have another molecule where these two directions are switched, because then the this cyclic structure has to break. And if that breaks, then that's not a stereoisomer, that's a structural isomer. Okay, because in stereoisomers you're not breaking any bonds. The other isomer only has directions that are different. So in cyclic structures, you can't really, I mean, you can't have versions where the sides are switched, because then it's no longer going to be a cyclic structure. Do you get this point? Isa, Mohammed, Ethan, do you get this point?
Yes.
Yes, sir.
So now I'm going to do some examples. Let's say I have but1ene and but2ene, and I want to figure out which one out of the two can form stereoisomers. It's going to exist in two versions. So but1ene or but2ene. Now but1ene is that you have four carbon atoms, and between the third and fourth, or the first or second, you have the double bond, and they are hydrogens. Now tell me, does it meet the conditions? Will it form cis and trans isomers?
No.
See, it's not going to form cis and trans isomers. The first condition is fulfilled. There is a double bond, but the double bonds have to be bonded to two different groups. Over here, you have a carbon that's bonded to the same group. So even if you make a three-dimensional structure of this molecule, and remember the three-dimensional structure, start by drawing a double bond with fan-shaped bonds or angles at 120 degrees. On one side, there is a CH, there is a CH2 and a CH3. On the other side, you have two hydrogens. Now, if there's another version where the hydrogens are switched, it still remains exactly the same. So the two sides have to be different on both sides. Okay, they have to be different, so that there could be another version. Now, butene is going to form stereoisomers. How can it form stereoisomers? It's going to have four carbon atoms. There would be three hydrogens, one H. Now, this molecule has a double bond, and each carbon atom is bonded to different groups. This side is also different. So if I'm asked to draw the molecule, you can draw the double bond with the fan-shaped bonds. One side has a H and the other side has CH3. This carbon side also has an H and a CH3. There's going to be another completely different molecule which would be connected in exactly the same way, H and CH3, but one of the sides would be pointing in or it's going to be switched in that molecule. So which one do you think is cis and which one is trans?
The first
Second
one
one
is
is cis.
cis.
ठीक है कौन सा ऐसा कौन सा
So second one
ठीक है so
is
second one
cis.
the second one is cis Ethan Mohammed
The second one is
Yeah.
trans because they're facing
Yeah.
other way, opposite ways.
okay ठीक है ऐसा remember this when they're pointing in the same side that's cis ठीक है I mean the H's are pointing upwards and the
Okay,
CH3s
sir.
and over here the CH3s are pointing in opposite direction one is up pointing upwards the other one is pointing downwards so this is going to be your trans version ठीक है so one is cis-butene I mean the proper name of the molecule is going to be cis Mohammed is this clear
Yes.
and this one would be transbutene. So that's how you're going to name the molecules. So look for these double bonds, and whenever you see those double bonds, make sure that the sides are switched or not. Let's do one more example. Let's say I have one chloropropene. I'm not sure if it's going to make it. Let's draw this molecule. So let's say I have one chloropropene, which means this prop, which is 3, and ene, that means double bond, and 1 chloro, that means on the first one there's going to be Cl and H and H and CH3. Now, can anyone tell me, is this going to form a cis and trans isomer, like in 3 dimensions?
No.
The other conditions?
No, the conditions are met, I think.
Yes, I mean you have a double bond, and each carbon atom on the double bond must be bonded to two different groups. I mean, so this side is also different, that side is also different. Okay? So remember, these sides they don't have any. I mean, they don't need to have a relationship between them. Okay? It's you have to check independently. These two need to be different, and these two need to be different. Um, so this molecule is going to have cis and trans isomers. Double bond, draw double bond, fan shaped. On this side, there's Cl and H, and on that side, there's H and CH3. Which version do you think I've drawn?
The trans.
Okay, it is the trans because the same type of groups are pointing in opposite direction. So this one is trans. And there's going to be another version of the molecule where this side, let's keep it as it is and switch the direction of the other side. So CH3 points upwards and the H points downwards. Now both hydrogens are pointing downwards or the same side. So that's your cis version. ठीक है, Mohammed, is this clear? Isaac, clear?
Yes, sir.
So only one of them has to be the same, like H and H. So the others can be
Yeah,
different.
I mean, there's another thing that all 4 can be different. Even then, it's going to form cis and trans isomers. But when all 4 are different, then the naming kind of changes.
Oh,
It's no longer. I mean, it's the same exact concept, but they won't be called cis and trans. The naming changes to E and Z, uh, and that's not in your course. Is that clear?
Yes.
oh, so the ones where all the groups are different is not in our syllabus.
Yeah, but it's exactly the same concept. I mean, the same thing would apply, right? There are going to be 2 versions. What you just need is that you need a double bond. These 2 must be different, and these 2 must be different. So, that's the only requirement. Uh, in our course, we just have cis and trans naming, but all 4 can also be different. Okay? Even the same concept would apply, except that the naming would be slightly different. Apart from, well, they won't be called cis and trans; they would be called E and Z, and in that has different rules which are not in your course, right? Okay. So moving to the next, moving to discussing more of the same. Uh, what if a molecule has multiple cis-trans arrangements? Let's do one example of a molecule that has multiple cis-trans arrangements. You can just hold on 1 minute. Now we're going to talk about multiple cis-trans in a molecule, and we're going to talk about unsymmetric alkenes first. Unsymmetric around the double bond. What that simply means is that if you kind of look on the left and right side of the double bond, you see different things. So this is an unsymmetric alkene. The right side is different, the left side is different. And I'm talking about unsymmetric molecules actually. So if you like divide the molecule into two, the right and left sides are actually different. So I'm just going to correct myself. I'm not talking about unsymmetric alkenes. I'm talking about the whole molecule being unsymmetric. You get the point what unsymmetric is? Ethan, Mohammed, is this clear? Isaac, clear?
Yep.
Yes.
Acha,
Yes.
so what's going to happen? First, tell me, is the first double bond making cis and trans isomers? Is it fulfilling the conditions? Like this carbon atom.
Yeah. Yep.
So this carbon atom is bonded to two different groups, and the other carbon atom that's also bonded to two different groups. Okay, so you're going to think of this whole thing as one group because it's attached to this carbon atom. So differently, it's going to form cis and trans arrangements, right? Um, let's rub this off. What about the other double bond? Okay, if you look carefully, that one would also form cis and trans arrangement because if you look around the double bond, both carbon atoms, this one is bonded to two different groups, and this one is also bonded to two different groups, right? So that's also going to be forming a cis and trans arrangement. So both of them exist in cis and trans forms. Two different three-dimensional forms, cis and trans. So I'm going to start. I'm going to draw these molecules now. Uh, now, how many total combinations would you have? Think of it this way: that this in a three in the this is not the actual three-dimensional shape, but in the three-dimensional shape, this could exist in two forms, and this could also exist in two forms. How many combinations do I have? Any idea?
4.
Okay, so you're going to have four. Either both of them are in cis arrangement, or the first one is in cis arrangement and the second one is in trans arrangement, or the first one is trans and the second one is cis, or both of them are in trans arrangement. So there are a total of four different combinations. So I'm going to just pick one and I'm going to try and draw the three-dimensional shape of the molecule for that one. Let's say both of the double bonds are in cis arrangement. So I'm going to keep the first one in cis. So first thing is double bond in three dimension. It's going to be fan shaped. Uh, there's an H and a Cl. So there's an H and a Cl on the first carbon atom, and on the second one there's an H. I'm going to keep that as cis. So that the H's point in the same direction. So on the second one there's an H. So I'm pointing the H upwards, and the other side is this thing. It's a CH. So you start off with the next double bond, and the next double bond can also have. Right after this carbon atom, you get this next double bond, right? So that is also going to be fan shaped, trigonal planar, and I'm keeping that as cis as well. So this carbon atom would be bonded to one H. The other carbon atom is also bonded to an H. So I'm going to keep the H's on one side, and the other carbon atom is also bonded to Br. So point the Br over there. So this is also your cis version. So the three-dimensional shape of the molecule would look like this, that both double bonds are in cis arrangement. Is that clear? Isa, Ethan, Mohammed, is this clear?
Yes.
Yes, sir.
Yep.
And then similarly, you could have the first one as cis and the second one is trans. So there could be another version of the molecule where the first one is cis. How do I make the second one trans? If I want to make it trans, I would, in this other molecule, the H and Br would be pointing in some other direction. I mean, the Br would be pointing downwards and the H would be pointing upwards. So that would make this, instead of a cis arrangement, it would make it a trans arrangement. Okay, so now this is the cis and trans version. Is this clear as well? Mohammed, clear?
Yes.
So, any questions about this?
No.
I said now,
No.
okay, now, Ethan, do you have any question?
No. Oh,
Now, tell me, how many arrangements would the molecule have if it was symmetric? If the molecule was symmetric, so if I want to make the same molecule symmetric, I think instead of the Br, there should be Cls on both sides, right? So there's a Cl here, there's an H, and an H, and an H, and H and Cl. So this molecule over here, now the molecule is kind of symmetric, and the cis and trans, this one would exist as cis as well as trans form. There would be two forms of this, and this double bond is still cis and trans, right? Now, what happens if the molecule is symmetric? Okay, let me first explain to you what would happen. When you have a symmetric molecule, looking at it, if there's a person standing over here and there's a person standing on the right side, for both of them, the molecule would look exactly the same. Do you get my point?
Yes.
Okay, so you're either looking at the molecule. I mean, if you flip it around, okay, you pick this molecule up and you flip it around, it's going to look exactly the same. The left and right sides are exactly the same. Okay, Aiza, Mohammed, Ethan, is this clear?
Yes, it's clear.
So what's going to happen is you still have four arrangements. Like there's going to be cis. The second one is also cis. You would have cis. The second one is also the second one could be trans. The first one could be trans, and the second one is cis, or both of them could be trans. Right? So there are four arrangements. But tell me which two arrangements are exactly the same?
The cis-trans
Cis
and
and trans.
trans.
Okay, exactly. Okay, if you pick this molecule up, because I told you, if I pick this molecule up and I just rotate it, it's going to be cis and trans. I mean these two, the middle ones are exactly the same. You get left to right, right to left, the molecule looks exactly the same. So that's basically one version. So in total, you're going to have three arrangements now. Right? Is this point clear?
yep.
Yes,
So
sir.
it's both the same, then it's one version only.
Yeah, it's. I mean, if you draw cis and trans, or you draw trans. I mean, let me draw both of them. Okay, let me draw both of them, and you'll realize that if you flip one around, it would look exactly like the first one. So they're basically the same versions. Let me do this quickly. You have. I mean, the first one is cis. So there's H and Cl, and there's H, and you reach the next double bond, right? And the second one is trans. So there's an H over here, and I'm going to point the H in the other direction. So this is cis and trans, right? So this part is cis, and this part is trans. Ethan, is this clear?
Yep.
The second version. The second version is, then you reach the next double bond, Now the second version is trans and cis. So there's an H over here, so the other H is over there. There's a Cl here, and this one I'm making cis, right? So look at both of them. They look different. Right now they look different. I mean, this one is trans and cis. Ethan, they look different, right?
Yeah, they do.
They look different because the cis arrangement, the Cl is not pointing downwards. In the cis, it's pointing downwards. In the trans, it's pointing upwards. But if I pick one of the molecule and I flip it around, okay, let's say I pick this one and I rotate it. I'm not changing anything. I'm just flipping it around and I'm putting it like this, right? Now compare the two molecules. They look exactly the same. I mean, the Cl is pointing upwards, right? Over here, the Cl is also pointing upwards. Over here, the Cl is pointing in this direction. Over here, the Cl is also pointing in this direction. Ethan, do you get my point?
Yep.
So basically, that means cis and trans and cis were exactly the same thing. You weren't drawing two different things. You were drawing exactly the same thing. Is this clear to everyone? Isaiah, is this clear? Mohammed, is this clear?
Yes, that's clear.
So now,
Sir,
yes.
Would that be possible? Huh. Would that be possible to have three double bonds?
Yeah, I mean, I'm coming to that.
Three
So what if
double
we have three double bonds?
No.
So three double bonds, and each one is making cis and trans. Each having two arrangements, cis and trans, right? So drawing them would take a lot of time. So we'll just discuss it. I mean, molecules can have many double bonds. Like organic molecules are very very large, and they have lots and lots of double bonds. Now remember, nature is very specific about the type of double bond. Like like most of your molecules, they have lots of double bonds, and each time the Cl would be pointing in exactly the right direction. Okay? The information is coded in your DNA, and the DNA tells the cells construct the molecule, and every time the molecule is constructed precisely the same way. So, so just imagine the complexity that we, with just two double bonds, things got really complex. I mean, there were four different three-dimensional shapes. Now imagine what nature is doing with the human body or with all the living organisms, that it has to make, not just make the right molecule, it has to make the right shape of the molecule. Like the same molecule can have many different shapes. So tell me, how many arrangements would be possible for three double bonds each? I mean, imagine a molecule with three double bonds, each one making cis and trans. Like there's a first double bond, it could exist in two versions. There's a second double bond, and it's an unsymmetric molecule. So the left and right sides are different. And there's a third one with cis and trans arrangement. So can anyone tell me how many different versions would exist? Like all three could be cis, right? The first one is cis, the second one is cis, and the third one is also cis. Or you could have the first one as being cis, the second one could be cis, and the third one could be in trans version, right? So how many total combinations do you have?
6.
No, not six. It's a cis, cis, cis.
Isn't it?
It could be cis, cis, and trans.
Well,
Not 12. So it could be cis, trans, and cis. It's basically related to probability and your combinations and permutations if you've studied
Is it
that.
24?
No, not 24. It's going to be
Okay.
9.
8. TK, it's going to be 8. I mean, you can draw all of them, TK. It's going to be cis, trans, and trans. I mean, you can keep drawing all the combinations. Basically, it's 2 to the power 3. TK, that's the formula. That that simply tells you. So that simply tells you how many cis and trans versions of the molecule would there be. And what is 3? 3 is So three is the thing. Three is the number of cis-trans double bonds. So it's going to be eight. Like you can write down all the combinations. I've written down four of them. The other four would be that the first one is trans. So you're going to get four more combinations with the first one being trans. So with a molecule having three double bonds, they're going to be there's going to be how many? Eight arrangements. What if a molecule has five double bonds,
Two power five.
which is 32, I think.
32.
Okay. Now imagine that most organic molecules they have lots of double bonds. Like 2 to the power 20 is if you do 2 to the power 20, like if something has 20 double bonds and each one has a cis and trans version, so 2 to the power 20 is a very, very big number. So a simple molecule with a simple formula can have many, many, many versions, many different three-dimensional arrangements. So 2 to the power 3. So just remember this formula. If somebody is going to ask you a molecule with four double bonds, it's going to be 16. 2 to the power 4 is 16. Is this clear?
Yes.
So this is cis and trans. And remember that all isomers, whether they are stereo or whether they are structural, they're going to have different physical and chemical properties. Like even here, some molecules would be polar and some would be non-polar. Like even with I think we did discuss this. Maybe, I mean, look at this one. Okay, for example, this is cis and trans. The Cl is pointing downwards, so that's a polar molecule. Over here, the dipoles are canceling out. The Cls are pointing in opposite directions. So the physical and chemical properties, although they're going to be there's going to be some similarity, they're not going to be drastically different. But all structural isomers, their properties are different. Okay, the physical and even the chemical properties are different. Now we're going to move towards the other isomer, which is known as the optical isomer. And they're known as enantiomers. So they're known as enantiomers. Uh, what are optical isomers? The conditions. It has to be sp3 hybridized. It has to be. That's the first one. The second point is that it has it needs a chiral carbon. So what's a chiral carbon? A chiral carbon is a carbon atom bonded to four different groups. So chiral carbon that's bonded to four different groups. sp3 simply means that it has to be tetrahedral. The arrangement has to be tetrahedral arrangement, and all of the bonds are going to be single bonds. Now, the best example of optical isomer is that there are two versions which are non-superimposable mirror images of each other. Non-superimposable mirror images. The best example of a optical isomer are your two hands. Okay, your two hands they look exactly the same, except that the orientation of the fingers is drastically different. Okay, no matter how you place or rotate one of your hand, it never looks exactly like the other hand because either the thumb would be pointing in the wrong direction, or your palm would be facing the wrong direction, or your fingers would be facing the wrong direction. something would be pointing always. I mean, no matter what you do, your two hands they would always be different. So the superimposable mirror images, and this only happens when you have a chiral carbon. So let's say you have a molecule, a carbon atom. This is how your chiral carbon atom would look like. It's going to be tetrahedral, and it's going to have four different groups attached to it. Like there is CH3 and there's H and there's uh, let's say there's CH2 and CH3, a bigger carbon chain attached to one of them, and there is a Cl atom, right? So there are four different groups that are attached to it. Now this molecule is going to have a mirrored version of it. Okay, what happens in a mirror? The left and right sides they are switched. So there's going to be a mirrored version of this. So the CH3 is pointing upwards. The H is pointing in this direction. There's a Cl which is pointing in this direction, and there's a CH3 or CH2 or CH3 that would be pointing over here. So this is what happens in a mirror. Left and right sides get switched. So this is what you see in a mirror. Now, these two are completely separate molecules. They have nothing to do with each other. This is one version of the molecule, and this is a completely separate, a different version of the molecule. Now, they look almost the same. Okay, just like your two hands, they look almost the same, except for the fact that the bonds are pointing in the wrong direction. And no matter if you pick this molecule up and you try to rotate this around, it's never going to look like this molecule. I mean, you can try this. Think of this as a three-sided pyramid with this wedge-shaped bond that's coming towards you. If you look at this, you would notice that if you try to spin this around, the bottom part, if you try to rotate this pyramid and try to bring the CH2, CH3 to the other side, then the Cl would be pointing in some other direction. Like if you try to change the direction of this bond, the direction of the Cl bond would also change. So, so something, if you try to correct one bond, some other bond might change position. Is that clear? Mohammed, Ethan, Isa, is this clear?
Yes,
Yep.
sir.
Yes.
Acha, so in any molecule, you just find, you'll be asked to draw these a lot. You just find these chiral carbon atoms because the isomerism exists around them. Okay, try and locate these chiral carbon atoms in a molecule. Uh, so, for example, I'm just going to give you a small question. Let's say you have uh, two 2-hydroxy, not 2-hydroxy. Let's make it butane 1,3,1,2 diol. So try and find or draw the molecule. I mean, this is your assignment. Try and draw the molecule. Find the chiral carbon atom and draw the chiral carbon atom the way I've done. Okay, draw two mirrored versions. Is that clear?
So the chiral carbon has to be in a tetrahedral structure.
I mean, it has to be it has to be sp3 hybridized, which means that it should be making four single bonds. Basically, what that simply means is that it should be making four single bonds. Or just look for a carbon that's bonded to four different groups. Is this clear?
Yes. Okay.
So we're going to continue with this tomorrow then, T. Okay then.
Yes. Okay.
Take care. Bye bye.
Yes, thank
Allah
you.
Hafiz, sir.
Allah Hafiz.